Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on problems on harmonic function. Today I am going to solve some problems on harmonic function. Already the definition and discussed in the last session, and also we have solved some problems. And now first, what is the definition of a harmonic function? For example, we have a function u of x comma y is said to be harmonic if it satisfies the Laplace equation. Laplace equation. What is that Laplace equation? Del square u equal to 0. So that is dou square u by dou x square plus dou square u by dou y square equal to 0. The sum of the two second order partial derivatives must be equal to 0. So to show that the function u is harmonic, we need to find the second order partial derivatives, and by adding those two, the result should be 0. Here we can verify whether the given function is harmonic or not basing on this definition. And also, if we have an analytic function f of z in the form of u plus iv, where u and v satisfy Laplace equation, then u is said to be conjugate harmonic function of v, and v is said to be conjugate harmonic function of u. So u and v are said to be conjugate harmonic functions. Now, for example, if a harmonic function u is given, we can find its conjugate harmonic function also. We can find its conjugate harmonic function v. Similarly, if v is given, we can find u also using the previous Milne-Thomson method, or else direct method also. We can evaluate the conjugate harmonic function. So let us discuss about those problems on harmonic and conjugate harmonic function. The first one, verify that u equal to x square minus y is harmonic or not, and also find its conjugate harmonic function if it is harmonic. The first one is harmonic, then we need to find its conjugate harmonic function also. So given, what is the given? U x square minus y. To check whether it is harmonic or not, we need to find its second order partial derivatives with respect to x and y. So let us find dou u by dou x with respect to x. So here 2x, whereas the remaining are functions of y, so we treat y as constant and the derivative of constant is 0. That implies again differentiating dou square u by dou x square is 2. Similarly, dou u by dou y with respect to y, the first one is constant, so 0, minus 2y minus 1, and dou square u by dou y square, the second order derivative with respect to y, minus 2, and for its minus 1 derivative is 0. So this is equation 1 and 2. Adding 1 and 2, dou square u by dou x square plus dou square u by dou y square is 2 minus 2, which is 0. That implies del square u is 0. Hence, u is harmonic. So it is very simple to check whether the given function is harmonic or not. Find the two second order partial derivatives and add them. If the result is 0, the function is harmonic, otherwise it is not harmonic. Now, also find its conjugate harmonic function. So that means we need to find v such that f of z is u plus iv. Let f of z equal to u plus iv, where u is x square minus y square minus y, and v it is required to find, and here u is already harmonic and this function itself is analytic. So to find this unknown function, again we can use the previous Milne-Thomson method, or else by direct integration method also we can evaluate this v. So let us apply that Milne-Thomson method first. In Milne-Thomson method, we consider f dash z. So we have f dash z is dou u by dou x plus I into dou v by dou x. But here v is unknown. Using CR equations, what are CR equations? Dou u by dou x is dou v by dou y. This is the first one, and dou u by dou y is minus dou v by dou x. So we can replace this dou v by dou x by minus dou u by dou y. So dou u by dou x minus I into dou u by dou y. So we have dou u by dou x and dou u by dou y. Just now we have calculated. First, dou u by dou x is 2x and minus 2y minus 1. 2x minus I into minus 2y minus 1. So this is 2x plus I into 2y plus 1. Now, by Milne-Thomson method, replace x by z and y by 0. Then what we get? F dash z equal to 2z plus I into y by 0, 0 plus 1. So that implies f dash z is 2z plus I. This is the analytic function. Now, by substituting z equal to x plus iy and splitting into two parts, real and imaginary, we can find that second function v, which is the conjugate harmonic function of u. So let us substitute z equal to x plus iy. Then f dash z. Okay, before that, first we need to find f of z. After that, we substitute z equal to x plus iy. Okay, let us start from here again. So f dash z is 2z plus I. Now, integrating on both sides, we get integral f dash z is equal to integral 2z plus I dz. So on LHS, the integral and derivative gets cancelled. So therefore, we get f of z equal to 2 into integral z dz plus I into integral dz. So 2z plus I. So this is 2 into z square by 2 plus I into z. So z square plus iz. Now put z equal to x plus iy. So f of z equal to x plus iy whole square plus I into x plus iy. So this is a plus b whole square, x square plus I square y square plus I into 2xy plus ix plus I square y. Just simplification. So here we can write the real parts first and then imaginary part. So x square is the real part, I square is minus 1. So x square minus y square. Again here I square minus 1 minus y plus I common x plus 2xy. So which is in the form of u plus iv, where v is x plus 2xy is the conjugate harmonic function of u. So using Milne-Thomson method, we can find the conjugate harmonic function also, just using the same procedure. Or else there is an alternate method. What is that method? We have dou u by dou x 2x and dou u by dou y minus 2y minus 1. By Cauchy-Riemann conditions, dou v by dou x is minus dou u by dou y. So I can substitute that here, 2y plus 1. So I have dou v by dou x is 2y plus 1. Now integrating with respect to x on both sides. Here, since we have partial derivative, so we can treat other independent variable as constant. So on LHS I will get v, and here 2y into integral dx remains. So that is equal to x plus integral, again the same, 2yx plus x plus some function of x. Now we need to find this f of x also. We can find dou v by dou x. So this is the function v, 2yx plus some function of x. So here we can treat it as a constant also. We can find this value phi of x. If this phi of x, the constant is 0, then the function is the same, v equal to x plus 2x phi. So that also we can, again differentiating this with respect to y, and we can compare it with dou v by dou y because that value is 2x, or else with respect to x compare with this one. So like that you can calculate that constant also. So either Milne-Thomson method or else using this alternate method we can find the conjugate harmonic function. Similarly, let us discuss one more problem on the same method. So show that the function u equal to e power x cos y is harmonic. First we need to prove that this function is harmonic. So for that, let us find the partial derivatives. Dou u by dou x with respect to x, so cos y is constant, and the derivative of e power x is again e power x, so e power x cos y. Next, with respect to y, e power x into derivative of cos y is minus sin y, which is equal to minus e power x sin y. And the second order derivatives with respect to x and y, dou square u by dou x square. So again differentiating this with respect to x, we get the same function e power x into cos y, and dou square u by dou y square. So minus e power x into derivative of sin y is cos y. So this is 1 and this is 2, adding 1 and 2. The LHS is dou square u by dou x square plus dou square u by dou y square, which is e power x cos y minus e power x cos y. These two gets cancelled, is equal to 0. So del square u equal to 0. That implies u is harmonic. Now we need to find its conjugate harmonic function also. So for that, let us apply Milne-Thomson method. Consider f dash z equal to dou u by dou x plus I into dou v by dou x. But using the CR conditions or CR equations, dou v by dou x is minus dou u by dou y. So by replacing the second term by this minus dou u by dou y, we get f dash z equal to dou u by dou x minus I into dou u by dou y. And what is dou u by dou x? E power x cos y. So e power x cos y minus I into dou u by dou y minus e power x sin y minus e power x sin y. So simplifying this, we get e power x cos y plus I sin y. Now this f dash z must be in terms of z. So by Milne-Thomson method, we have to replace x by z and y by 0. So x by z and y by 0. Then f dash z becomes e power z cos 0 plus I sin 0. So cos 0 is 1, sin 0 is 0. So we get e power z. So that means f dash z equal to e power x plus iy, which is e power x into e power iy. So e power x into what is e power iy? E power I theta is cos theta plus I sin theta. So e power iy is cos y plus I sin y, which is e power x into cos y plus I into e power x into sin y. So this is in the form of u plus iv. So hence the conjugate function v is e power x sin y. This is the conjugate harmonic function of the given harmonic function. So this is the method of finding the conjugate harmonic function. So the Milne-Thomson method helps us in finding the conjugate harmonic function. In today's session, we have verified whether the given function is harmonic or not. Harmonic or not. And also its conjugate harmonic function can be found using the Milne-Thomson method. So the Milne-Thomson method is useful to evaluate the analytic function whose real or imaginary part is given, and also to evaluate conjugate harmonic function. Conjugate harmonic function. So in these two cases, we can apply the Milne-Thomson method. So this is for today's session, and we will meet in the next session. Thank you.